With us today, we have Francisco José Díaz-Galiano, and he is coming from the University of Almería. And today his discussion will be on time of flight mass spectrometry applications in food science, looking at targeted and non-targeted approaches. So the instrumentation that he's going to be talking about is our TOF, and he's going to give an overview of the practical targeted and non-targeted workflow approaches for food analysis using the high-res technology. And he's also going to talk about some of the SWATH work that he has done with the TOF. So I will hand it over to you, Francisco. Welcome, and looking forward to hearing your discussion today.
Thank you very much for the introduction of the presentation, for my introduction, and for inviting me to being here today. So the topic has been greatly introduced already. So I'm going to go ahead and start with the talk about the work that we developed in targeted and non-targeted applications using time-of-flight technology, both the Xenotop 7600 and the X500R. I'm going to start with the targeted methodology first. This work was recently published in the Atlanta Journal as an open access, where most figures and additional details can be found. In the first half of the talk, I'm going to discuss the development of the SWATH DIA method, which uses the xenopulsing technology. And I will go into the details of the method development, optimization, and all the issues that we had and how we overcame them. And then I will move on to the non-targeted approach. So the instrument configuration we employed is shown here on screen for the targeted approach. On the LC side, we used methanol and water as our solvents, with formic acid and ammonium formate as the solvent modifiers, and we employed a core shell column. And regarding the HRMS device, this work was based on the Xenotop 7600 kit-off. It was operated in full scan mode in the range of 100 to 1000 NT-Z ratio, with an accumulation time of 80 milliseconds, and the XenoSWATH DIA approach for the MS2 was operated with an accumulation time of 50 milliseconds and 9 SWATH windows. Regarding the specific configuration of the SWATH mode, initially the 9 windows were equal to one another with a width of 100 MTZ ratio. To begin our experiments, we employed a mixture of all pesticide residue standards that were potentially amenable by electrospray ionization in the positive mode, with a total number of 282 compounds, mainly parent compounds, but also some metabolites as well. Since we were developing the method from scratch, it was also necessary to create the processing method as well as the acquisition method that I just showed. For this reason, we injected the pesticide residue mixture in solvent, in acetonitrile and water at very high concentration using an IDA approach. And then we manually revised all the experimental IDA spectra and used the fragments we found to build our pesticide residue database. In the end, accounting for both precursor ions and fragment ions, we ended up with a database of about 2,800 ions that we employed for further method development. So once we had built the database, we began evaluating the performance of the method. First, we prepared a tomato extract using the Ketcher's methodology without a cleanup step. And then we prepared a calibration curve on this blank extract, going from 0.5 micrograms per kilogram all the way up to 500 micrograms per kilogram, or ppbs, as I will probably refer to during this presentation. As shown in this figure, the precursor ion for almost 42% of all pesticide residues could be detected at the lowest concentration level at 0.5. The cumulative data makes it easier to observe that almost 84% of compounds could be adequately detected at 2 ppb and 93% at 5 ppb, with almost 97% presenting good peak shapes and mass accuracy at the 10 ppb level. Now, moving to the detection of 2 ions with mass accuracy under 5 parts per million or under 1 millidalton for ions under MTZ of 200, the figure on screen shows that almost 60% of pesticides could be adequately detected at 2 parts per billion. And again, looking at the cumulative data, in this case, for the detection of 2 ions, over 91% of all pesticide residues could be detected at the 10 ppb concentration level. This good performance of the Q-TOF device is due in great measure to the xenotrap. The xenotrap, as you already know, accumulates ions in a step prior to their separation in the time-of-flight tube, thus increasing the sensitivity of the subsequent mass experiment. The beneficial effect of the trap can be, of course, assessed by comparing peak areas with the xenotrap on and the xenotrap off. However, another way in which the increased sensitivity becomes apparent is when looking at the source of the most intense ion for any given compound. So we manually checked which one was it. In the case of the precursor ion, for 1 in 6 compounds, the precursor ion in the MS2 SWATH experiment was more intense than in the actual MS1 full scan experiment. Moreover, for more than 50% of all pesticides, the most intense ion was not found in the full scan method, the precursor ion, but rather it was a fragment ion found in the SWATH experiment. What this means is that the precursor ion found in the full scan experiment is the most intense ion only in 1/3 of all compounds, rather than being the most intense ion overall, as is typical in methods based on high-resolution mass spectrometry. So for 2/3 of all compounds, the most intense ion was either a fragment or the precursor ion, but found in the SWATH DIA experiment. Now let's see an actual experiment of this scenario. Here we have the extracted ion chromatograms of bromoconazole, which is a mixture of 2 isomers, the E and Z. It's resolvable, that's why we are seeing 2 peaks. And on the left, in blue, we have the extracted ion chromatograms of the precursor ion in the full scan experiment. And on the right-hand side, we have the extracted ion chromatogram of the precursor ion, but in the SWATH DIA. This means after fragmentation. So if you pay attention to the signals here pointed by the arrow, you will observe that after fragmentation, it is still 20% more intense in the SWATH DIA experiment than in the full scan experiment. And as I just discussed, this situation was not uncommon at all, showing the increased sensitivity of the xenotrap. Another parameter that we investigated was the linear range. And as I'm showing in this slide for pyriproxyfen, we found that many pesticide residues presented very good linearity across 3 orders of magnitude, that is from 0.5 to 500 ppb. This was true for the full scan analysis. However, there were some differences for the MS2 data. As originally described by Loboda and Chernusevich, I hope I pronounced that correctly, when discussing the fundamentals of the xenotrap, its use can be subject to peak saturation and the loss of mass accuracy. But this is not a problem of the xenotrap itself, but rather from the detector, the time to digital convector, and the dead times that can appear when one has a very high ion currents. So in this slide, you may observe how the linearity and mass accuracy are lost for the pyriproxyfen fragment, but this situation can be overcome either by turning off the xenopulsing option in subsequent experiments and running the sample again, or by creating a specific MRM-HR method for the confirmation of fragment ions. But moreover, we have to keep in mind that this is a targeted approach. So we are running our calibration standards alongside our samples, and we have our compounds of interest. So for any given concentration, for any given compound, we can check if the mass accuracy is also being lost for the for our calibration curve at the suspected concentration. And moreover, we can also check at the beginning and at the very end of the elution of the compound what the mass accuracy is, to check whether this is one of these dead time effects or it's just another compound altogether. And always remember that the full scan method is going to be unaffected by this. So returning to our pesticide list, we began working on improving the data that I have shown you before. To this end, we plotted the density distribution of all precursor ions to find the M to Z ranges where the greatest number of precursor ions could be found. And we found that the average M to Z ratio was 334. So then we reorganized the SWATH windows to improve the method by adapting the SWATH windows from fixed to variable. We attempted to reduce the background noise and interferences from colluting species. This would result in lowering the instrumental LQs and thus a better method performance. We began, as I mentioned before, with fixed 100 Dalton windows, and then we moved to these variable windows. The total cycle time, which was very good, 650 milliseconds, remained unchanged because what we were doing was just moving and reducing by 40% the width of the SWATH windows where we could find the greatest number of precursor ions. So we moved from the experimental configuration I showed you before on the top left to the new variable SWATH windows shown in the bottom right. And then we rerun our experiments of spiked blank tomato catcher's extract, and we found a significant improvement in the instrumental LQs. The new SWATH method resulted in a 5% increase of compounds detected with 2 ions at a concentration of 2 ppb, although it is true that this was not a night and day difference. Considering this very small change that we made to the method, we were very satisfied with the results. And again, when looking at the cumulative data, you can see that now we are at 87% of all compounds with 2 good ions at the 5 ppb level. And in practical terms, what does this change mean? Let me show you some examples that we collected during the method optimization. Let's begin, for example, with the triazoles. So triazole fungicides are a chemical family of pesticides with very similar physicochemical properties, and in most cases, their most intense fragment ion is the triazole moiety with an empty set ratio of 70, shown here on the right-hand side of the presentation. When analyzing triazoles using triple quad, you typically don't run into much of a problem because with the precursor ion, you can separate each of them and use the fragment ion. But when you are using xenoswath DIA methods, like in this case, the swath window will allow all precursor ions within the empty set range into the collision cell, resulting in the coelutions that you can see here in the chromatogram. But now, if you take a look at this chromatogram, you will see that with by modifying the swath windows, as we did, we can avoid many of these coelutions, allowing for the use of the best fragment ion in all cases, and better quantitation of the triazoles, such as this tebuconazole example shown here. Bromoconazole, which we discussed earlier in this presentation, is another clear example of how the optimization of the SWATH method can allow for better method performance. So here we can see that we have an interference that is giving rise to a 500 ppm mass error. But now with the new SWATH windows, we're removing these interferences and we're reducing the ppm from 500 to 2.3 ppm. Another interesting class of pesticides are the spinosins that previously fell within the same SWATH window. If the chromatic separation is not well optimized, as was in this case. So we can find ourselves with a situation where we cannot really analyze very well the spinosins because the fragment MTZ142 is the most intense and the most appropriate for each of them. Let me show you why exactly. Here, the graph on screen represents all the 4 spinosins commonly employed as insecticides with their main structural differences. So you will find the structural differences in the 6-member ring, and also on the substitution of the 3rd monosaccharide. In a spinetoram, we have ethyloxy group, and in spinosine, we have a methyloxy group. A critical aspect of the analysis of spinosins is that the 2nd isotopal log, shown here on the bottom right, of spinosine D is isobaric with spinetoram J. So the fact that this isotopologue exists may not be a big issue if it were not because, as I said, they share the most common fragment ion. So by placing the limit specifically now the 2 last SWATH windows at 747.5, We can now eliminate the spinosine D from the equation in the analysis of spinetoram J, although there is a very small signal due to this isotope log that I was mentioning before. However, due to the necessary overlap between the two consecutive SWATH windows, in this method it was not possible to overcome this interference for spinosine D, and it still remains a point to improve. But at any rate, it is a great example, I think, of how fine-tuning your SWATH DIA method can lead to better results in terms of avoiding coelutions and better LOQs. I'm going to show you some other examples that we found that were very dramatic from our point of view. So now we have difenoxaferone, which belongs to a different compound group, the ureas, and similarly to the triazoles, the ureas have fragment ion, the 72, which is common across them and is typically the most intense ion. So with our initial SWATH windows on the left, the most intense ion could not be used, but now with the new window configuration, we could lower the LOQ from 5 ppb to 2 ppb. Isoproteron is another urea, which was used until about 10 years ago in the European Union before it was banned. And again, the most abundant fragment ion with the new SWATH DIA configuration can be used for its analysis. Another good example of the removal of interferences is tebufempirat, moving from 5 to 2 ppb, and the removal of the coelutin interference. Another triazole is tricyclazole, which shows a dramatic improvement in the signal-to-noise ratio, moving from the old method to the initial method to the new method. Now you can see that there's barely any background noise for this fragment. Another example is the pyrethroid etofenprox. We are both reducing the background noise and removing interferences, improving its analysis. Another good example as oxyfluorphane is another case of the reduce of the background noise and improvement of the signal-to-noise ratio, even from 5 ppb, moving from 10 ppb to 5 ppb in the LOQ. And the last example I'm going to show is prasimidone. This chlorinated carboxamide also shows a substantial improvement in terms of signal-to-noise ratio. As you can see here on the left, it barely fits the criteria. I think it doesn't fit the criteria, whereas on the right, it fits perfectly well the signal-to-noise ratio. So the developed SWATH DIA method was then applied to the analysis of contaminants in baby food, a group of commodities where, as you know, the regulations are very strict. We narrowed down the method to 219 pesticide residues after the removal of those which are more amenable by GCMS, for example, or by the electrospray negative mode. And we also included 9 mycotoxins to this multi-residue method. The sample preparation was based on catchers and with micro-SP cleanup, and the details can be found in this online paper that I referenced before. This method allowed us to validate LOQs at 3 ppb for 81% of compounds and at 10 ppb for 98% of the target list. I'm going to show you now some details of interest. First, about matrix effect. We evaluated 3 different baby food matrices, which were first apple and banana, then pear, banana, oat, and lemon, and then also green peas, zucchini, and broccoli. And what we found when we evaluated the relative matrix effect, because typically a laboratory is going to run calibration curve in a given matrix, and laboratories, in my experience, are interested in knowing the relative matrix effect as well as the actual matrix effect. And as you can see here on screen, for almost all of them, 210 compounds approximately, there were no significant matrix effect across any of the matrices. Then we also evaluated the difference in signal intensity for the SWATH DIA method when using xenopulsing. This is an example of the dimethoate spiked at 3 ppb. And on the left-hand side, you can see the precursor ion at about 800 counts. And the fragment ion has approximately 25% relative intensity with the xenotrap off. Then we move to the right-hand side and analyze in the same spiked sample. You can see that the precursor ion stays at the same level as expected, and that the fragment ion almost triplicates its intensity. So this is going to make the identification of compounds both in targeted and suspect screening methods much easier than without the xenotrap. These graphs also show the difference the use of the XenoSWATH makes with real samples. These are real positive findings that we encountered. So on the top, we show 2 positive findings, trifloxystrobin and eniatina-1 in the real samples. And here on the bottom, again, you can see in blue how the fragment ion is significantly more intense, about 7 times for trifloxystrobin and about 2 to 3 times for the mycotoxin. And finally, what I'm showing here is another possibility for sample identification in cases where we may find interferences from the matrix at the MS2 level, or in which the signal intensity was too high for the XenoSWATH DIA method. So an alternative to turning off the xenotrap is using the xenotrap, but in an MRM-HR method. And in this way, we can obtain very pure MS2 spectra with very good intensity for all fragment ions, which is what we did for another positive finding. So everything I have discussed here and much more regarding the targeted analysis can be found in this publication that I showed you before. And now I'm going to move on to the second part. This will be a bit shorter than the first one, on the usefulness of QTOF HRMS to fight against fraud in valuable commodities. For this work, we selected a very valuable commodity, which is Manuka honey, which had recently been the target of fraudulent commercialization. Manuka honey is a type of honey produced mainly in New Zealand by honeybees foraging the Manuka tree. And indeed, with only 1,700 tons produced annually, about 10,000 tons were commercialized, which suggested that there was a problem with counterfeiting, that it was extremely common. So in 2017, the New Zealand government issued new legislation that required the presence of specific natural products at certain concentration thresholds, either in monofloral or in multifloral Manuka honey. The drawback of this approach is that these substances are freely available from many different vendors. Hence, they can be spiked into non-Manuka honey, and additionally, some of them are known to degrade somewhat fast, limiting the shelf life of Manuka honey. So for this work, we focused on monofloral Manuka honey because of its higher value. This time we used the X500R QTOF instrument with chromatographic condition similar to the ones that I presented before, just a longer chromatographic run because we're doing non-targeted analysis. And instead of SWATH acquisition mode, we run our samples in the information-dependent acquisition mode with a top 10 feature acquisition. So the first objective was to identify potentially new markers of Manuka honey authenticity. What I'm showing here are the loadings of the non-supervised principal component analysis. That is the principal component analysis built using all detected features, all detected ions. Their distribution on the graph corresponds to the weight on each principal component. Observing the PCA itself, not the loadings, we can see how even in this non-supervised PCA, Manuka honey is clearly different from the 3 honey types that we selected for the initial study, which were eucalyptus, chestnut, and avocado. And I forgot to mention that this part of the work was done on MarkerView software. Eucalyptus honey was the variety showing the greatest similarity to Manuka honey in terms of ions in the electrospray positive mode. And this situation also repeated in the electrospray negative mode evaluation. Again, eucalyptus was the most similar commodity to Manuka honey. The next step was the tentative identification of potentially new Manuka honey markers. As in all cases, this was the lengthiest and the most time-consuming step, and it required both in silico and manual fragmentation pattern evaluation. The 19 compounds could be loosely grouped depending on their structure into the groups that you can see here on this slide. So we wanted to also evaluate the exclusiveness of these natural products for Manuka honey. Several additional samples were acquired in a local supermarket, including new honey varieties, as you can see here on screen. The areas of all 19 compounds were normalized over the area in Manuka honey, which is set at 100%. And only 2 of the 19 compounds were found at greater concentrations in other honey varieties. The summary is shown in this slide. So there were 19 tentatively identified compounds. Out of these, 9 had never been reported before in Manuka honey, but they had been in other commodities, and 5 had never been reported to the best of our knowledge at all. This was the first time this feature had been described, and they were mostly exclusive to Manuka honey. In this situation, spectral arrays are not of much help, and identification must be performed based on the fragmentation pattern and in silico software. In this example, I'm showing one of these identifications. You can see how in the total ion chromatogram we cannot see any significant peak protruding from the rest, but thanks to the marker view evaluation, we found this precursor ion, and we were able to assign a structure to all of its fragments. And this was one of these compounds exclusive to Manuka honey. And moreover, some synthetic routes were also proposed because it's not only important to find these new compounds the first time you describe this structure, but also try to think where they can come from. And we found a way in which they could come from compounds that are known to be present in Manuka honey. So this was the last part on the natural product identification. With the new found markers alongside the 4 legally mandated ones, we set to evaluate possible fraud strategies. So first, we evaluated the spiking of the 4 legal substances on various honeys at varying concentration levels. Then we picked the closest variety to Manuka honey, the eucalyptus honey, and mixed it at a 50% ratio, and we also spiked these standards. And finally, we also did the same experiment with a 25% dilution in weight only, and also the spiking of the compounds between Manuka honey and eucalyptus honey. In a final step, we turned to our software to combine our electrospray positive and negative data, and I'm going to show here the supervised model showing striking differences. So these very long shapes that you can see here are due to the spiking of these compounds down and to the right. And the PCA model shows how most honey varieties, except for eucalyptus, are grouped together on the left, while the Manuka honey samples are placed on the right, so quite a different commodity. Moreover, this created model based on the 23 natural products allowed to differentiate authentic, non-adulterated Manuka honey even from the worst case scenario, which is 75% purity and the spiking of 4 legally mandated compounds. And when we remove these 4 legally mandated compounds and focus only on the 19 newly identified compounds, thanks to the Kitov technology, you can see how having them or removing them, the 4 legal compounds, makes little difference, and that Manuka honey can be very well differentiated using these features. And on a final note, I wanted to show you the difference. This is the last experimental slide I'm showing. The difference in the identification, which is based on the X500R, as I was saying, and the Xenotoph 7600. We ran our samples again in the same acquisition mode. And now I'm showing here the difference in intensity. We're talking about twice as intense thanks to the Xenotrap. And also in terms of mass accuracy, which was very good in the X500R. We're talking about very small molecules, very small ions, but except for 2 instances, in the rest of the cases, all ions were found with better mass accuracy using the Xenotoph than the X500, which, as I said, we were quite happy with the capabilities of the X500, but the Xenotoph was just on a better, much better level in terms of mass accuracy. Yeah, and the details of this work can be found in this additional paper. And for the conclusions from the non-targeted approaches and targeted approaches, In terms of non-targeted approaches, food authentication and biomarker discovery, QTOF-based high-resolution mass spectrometry enables the discovery of unique biomarkers, as I showed here. So we ran our data, we checked some databases, we did some manual identification of the fragments, and thanks to this, we were able to identify 19 new markers of authenticity for Manuka honey. The automated top-10 approach, top 10 IDA in this case, was great at surveying the mass spectra, the samples to final features of interest. And thanks to the sensitivity of this instrument, we were able to go very high sample dilution, because honey is a bit a matrix that's a bit complex. So we had to dilute our samples a lot. But thanks to the sensitivity, we didn't miss anything of importance, I think. And finally, regarding the targeted approach, the XenoSWATH DIA method allowed us to detect many pesticide residues and mycotoxins at LQs as low as 3 ppb. The optimized SWATH windows allowed us to reduce interferences, to improve the LQs and accuracy. We found no significant matrix effect for these matrices. And the detected contaminants can be further characterized via MRMHR experiment, which was quite helpful in some cases. And that's all on my part. Thank you very much for your time, your attention, and I'm here for any questions.